Okay. So, good afternoon. I think it is time to start. So, I'm happy to start this afternoon session. And I've titled my talk, these axionic waves as dark matter. Usually one talks about ways to detect them with physical experiments, and I will mention this. Now in our institute, we are part of the ICCUB collaboration, and so we're basically getting into this field of axion detection. And then I will mention also that astronomy may offer us some ways of detecting axions, which as a candidate of the dark matter. And to start with, I'll just say that, as you know very well, dark matter is a key question in cosmology, a very important one in physics too. We have all these observations that tell us that dark matter exists, right, in galaxies and cosmic microwave background, and that dark matter is 84% of all the matter in the universe, right? And this is the number that's important and is fundamental in our universe, not this other stuff about being dark matter being 25% of the total because there is dark energy that is repeated ad nauseum because, well, the time we live in is not a special one. So, this fraction of dark matter is the one that's independent of time, right? Doesn't depend on our time. So that's what's important. And it behaves as cold dark matter, meaning that initially it had very low velocity dispersion, and all the velocity dispersion of the dark matter that's anywhere in the universe is only the result of nonlinear evolution of things like galaxies and clusters of galaxies. So, dark matter is also non-baryonic, and we know this today because of all the observations of the CMB and the way we can reproduce the power spectrum of the CMB only with non-baryonic cold dark matter. So, see how this works. So this I'm showing you here, gravitational lensing. That's one of the evidences of dark matter, right? Look at this beautiful lensed galaxy here. It's an arc lensed by the gravity of the cluster of galaxies, which is here. So that's very nice, a way to measure that there is a lot of mass beyond baryons, but also, as you will see, this gravitational lensing will be relevant for what I'll say later. So, what could the dark matter be? We don't know, but I think there's three types of candidates, essentially, that we talk about. And correct me if I'm wrong, but I think it's just these three. It can be a new particle physics that is thermalized. That means it interacted at some point in the early universe, the history of the early universe. It must be massive. Then we talk about this weakly interacting massive particle, so that the velocity dispersion today is low, right? Because it was in thermal contact with the matter, then it has to cool down, and in order for it to be cold today, it has to be a massive particle. In my opinion, the problem I see here is that today we can ask what motivates the existence of yet another massive, neutral, weakly interacting, and non-decaying particle. Why would this particle not decay? Today, I think there's not so much motivation for this assumption, and basically, you can make models that satisfy this, but it's just for the purpose of explaining dark matter that you make such models. Similarly, with primordial black holes. Primordial black holes are very nice. Marcus since told us about it in the morning. They'd be made from radiation in the early universe, just collapse if you have these high amplitude fluctuations in small scales. But you can ask also what motivates the large primordial fluctuations that will be needed to form them at a specific mass scale, compared to the low amplitude we observe on large galactic scales, which make galaxies collapse, right? You have to have much higher amplitude at some small scales. And then if you go to even smaller scales, we know that at masses 10 to the 16 grams, there's very few black holes, because if they were there, they would be evaporating through Hawking radiation, and this would be detectable as gamma rays in the universe, and we don't see any of that, right? So it has to be that you make black holes, some scales between galaxies and these small 10 to the 16 grams, and again, you can make models, but it's not motivated by anything else than saying, oh, I want to explain dark matter. The third alternative is that it's a light particle, but it's created in it's not thermalized, cold state, so then it can be cold even to the particles very light, if it was never in thermal contact with baryons and radiation in the early universe. So then this would be, you create it in a cold state, which would behave like a classical wave with very high quantum occupation number. So if that's true, then, and that's the dark matter, then the dark matter is best thought of as a classical wave. So why do I think axions are the best dark matter candidate? Because the way axions were predicted, possibly they can exist. Of course, this has not been confirmed by any observation so far. Is that it's the prediction of an elegant model to solve this particle physics problem. The strong QCD problem that has been discussed before, having to do with the fact that Newton's electric dipole moment is 0. There is no CP violation in the strong interactions. Okay, I'm not going to go into this, but the problem is that the question is this prediction is unrelated to dark matter. It just comes from particle physics. Yeah, depending on the unknown axion mass. If this action exists, it would be created, it would account for the properties of dark matter, and for reasonable parameters, it can have today the dark matter density that is observed. So essentially, you solve particle physics problems, the consequence is dark matter would exist and would be accounted for these axions. So in this case, axion dark matter would be a pseudoscalar classical wave. It's interesting that the classical physics world has only one fundamental wave, with the electromagnetic field. Everything else is particles, or, for example, gravity is space-time curvature, right? So if that were true, then there would be a second type of wave, which is truly fundamental, behaving as a classical wave, which would be the axion field. And this would be the dark matter. So dark matter in galaxies would be just this kind of waves sloshing around, right? Like a field. And they would interact very, very weakly with the electromagnetic field. And with gravity, of course. So far, we would only have detected them with gravity. And axions at rest, you should just think of them, as this classical field, right, as a function of time. It oscillates with time with some frequency omega related to axion mass, right? But it would just behave as this classical field. Apart from the gravitational interaction, axion waves would have very weak interactions with this electromagnetic field, so Maxwell's equations would be modified, and this would offer us a way to detect them. So the way that has been explored for several decades about detecting axions is that, first of all, they would be produced in the sun, in the core of the sun, by an effect known as Primakov effect. Primakov effect is just a conversion of a photon into an axion. And its inverse is the conversion of an axion to a photon, which would happen once this axion from the sun arrives at the Earth. So if the axion goes through a magnet that you've got here, with a magnetic field that is as big as you can make it, and a volume that's as big as you can make it, then the axion goes through the magnetic field, and then there is an interaction of the axion field with the electromagnetic field, which means that as the axion goes through, it creates an electric field that's oscillating here at the frequency of the axion. And that's the modification you get of Maxwell's equations. And then this oscillating electric field can become photons. And then you have to detect these photons. In the case of axions from the sun, these axions would have the energy of the core of the sun, corresponding to X-rays. As the axions go through this, they would be converted to X-rays. But the conversion rate is very, very small because of the weakness of this interaction of the axion with the electromagnetic field. And then what you do is there's very few X-rays being made here, and they're all emitted in the direction coming from the sun. So here you put an X-ray telescope. It focuses the X-rays to a detector, and here you detect the X-rays. And the important thing is this has to be extremely low background noise, because you make very few X-rays here. So the key is reduce the noise as much as possible, so that if you detect an X-ray, you're almost sure it comes from an axion came from the sun. And this is, for example, being made in the YAXO collaboration. Okay, so this is the one way we could detect them, and also the way that the axions are produced here is very similar. So when a photon goes by the electric field of an electron or the nucleus in the core of the sun, is this strong electric field. Also, the photon can be converted to the axion, right? So then that's why these axions are produced in the core of the sun. The rate is very small. Here you also, the rate is very small, but you could, in principle, detect them. This is called a helioscope. If axions are dark matter, then there is a second thing we can do. We can detect the axions in the dark matter. And now these axions would be at rest. They would not have X-ray energies, but depending on the mass of the axion, for the masses that are now explored that would be consistent with what we know about dark matter, the density and so on, these masses correspond to, they're about 10 to minus 5, 10 to minus 4 electron volts. They would correspond to radio photons. So you have to basically detect radio photons that would be created here in a very different way with resonant cavities. Whereas in the case of the sun, they would be coming as X-rays because the action is highly relativistic, just coming from the sun and producing this energy. Okay, so one experiment that is proposed and trying to do this is this International Axion Observatory, in which the ICCUB is participating. And IAXO is basically this, it's called it's like a telescope. This is the magnet. You point it to the sun, and then basically the X-rays are collected and sent to these tubes here where you put the X-ray detector and so on. And here our institute is contributing to the data reading instrument for the initial. There's something called Baby IAXO, which is a prototype of the proposed IAXO, where we are contributing with some the data acquisition and the electronics to read the data that is generated by the X-rays here when they come to the detector and generate an electron cascade. And Eduardo Picatoste has been working on this. So this is an opportunity for anybody at the institute interested in this to analyze the data that this will generate and analyze this essentially axion telescope that looks at the sun to essentially understand what are the limits to which we can say if we have detected or not axions from the sun. But then there is also, as I said, the dark matter part. So axions we think would be the dark matter also, and then these axions are non-relativistic in the dark matter. They would be moving, they would be making the halo of the Milky Way, and therefore having the velocities typical of the Milky Way, about 200, 300 kilometers per second. So these non-relativistic axions, they would be essentially almost at rest. And the way to detect them is in the same magnetic field. Then you put a cavity like this one. This is a picture of a conducting cavity. In this case, it was split into 5 that are acting coherently. And the axions would have, you try to match their oscillating frequency to the size of the cavity, and they would be creating essentially photons inside this cavity. And this would be in the radio. So then, again, you have to try to reduce the background as much as possible. What you do is you put this conducting cavity in the magnetic field. You cool it down. Once it's very, very cold, essentially imagine that you could cool it so that there's no noise, eliminate any thermal photons, okay? Connect some cable or something that can detect if there is any radiation in there, and it would look like there's energy created out of nothing. Suddenly you put this cavity there in the magnetic field, bring the temperature down to a very, very low value, photons would be appearing out of nowhere. Well, actually it would be the dark matter, right, modifying Maxwell's equations in this cavity, creating an electromagnetic field that would oscillate, and then axions converting to photons. And that's what you would get. So essentially, this is Sergio Arguedas, who is there in the corner. Sergio is the expert in these experiments, and this is one that we're involved with is the RADES experiment, working with this type of cavities in magnets. And in the past, some data has been collected, which we're analyzing. And in the future, these cavities are being constructed, and they're going to be placed in various magnets where this kind of experiment can be done. Essentially, what happens here is that the electromagnetic field is being forced by the axion wave, which is the dark matter. And this greatly, if there is a resonance, this can increase this axion photon conversion and allow us to see if there is any axions detected which are producing, essentially photons. These photons that would be produced here by axions would be all having the same frequency. So you have to catch the photons at a certain frequency, which if it coincides with the resonance, the natural resonance of the cavity, then you can detect it. Okay, so that basically works as a forced harmonic oscillator. Okay, the harmonic oscillator is the electromagnetic wave, the standing wave in this waveguide here, and if the axion is forcing it, then it'll basically create this electromagnetic wave and produce photons. So then in this field, one always makes this plot about as a function of the mass of the axion in electron volts here, in this case going to from 10 to minus 6 to 10 to minus 4 electron volts, you put limits on the coupling of the axions to the photons. And so in particular, you know, so this basically determines what's the rate at which photons here are being created. Many experiments have produced these limits. At each frequency or each mass of the axion, you have a limit which an experiment has reached. It says, you know, this coupling has to be smaller than this, given our limit to the number of photons that are being created inside the cavity. But you basically work only at one frequency, because you have to build a cavity that resonates exactly with the axion. You can only look at one frequency. And so in this game, you have to basically scan this and explore all the frequencies, and this is very hard. And so far, Rades has only looked at one frequency, because we're not able to tune very much yet. But so we have this limit here. We have put this limit. And this is what we need to improve on. So we're just starting on this, as you can see. We plan to do work on data acquisition and analysis for Rades and future experiments. There's several future experiments which we are discussing. So finally, let me go to some astronomy considerations. Axions, in addition to being detected either from the sun or from the dark matter in these physics experiments, you might also detect them in a different way, using the idea that in most cases in these axion theories, the axions would be this dark matter that is formed in the early universe, in this cold state I was talking about, okay, and then they would not remain homogeneous, but typically this axion field would have its own fluctuations, small-scale fluctuations, right, like primordial fluctuations. The same way in cosmology, you have primordial fluctuations that make galaxies. So if you have this axion field, it might have its own primordial fluctuations on much smaller scales, and actually these fluctuations would be isocurvature, not the adiabatic ones that one usually considers. But in any case, the thing is that they would also collapse gravitationally to small mini halos, much smaller scales than galaxies, and also very early, because these fluctuations would be of order 1, but only on small scales. And so they would be collapsing, you know, redshift 3000 or 10,000. You would already have these mini halos being formed. The dark matter would be clumpy already, okay? But the masses would be these extremely small numbers, like asteroid-like masses, and size is about smaller than the orbit of the Earth. So instead of having this diffuse dark matter spread all over the universe, it would start getting these clumps. But these clumps are very hard to detect, right? So soon after this matter radiation equalization epoch, these clumps would be formed. They would just collapse and reach some sort of equilibrium, and then they would be essentially making mini halos. These mini halos would merge with each other, just like galaxies do, making bigger halos and so on. They would have the whole hierarchy. So today, much of the dark matter in galactic halos, like the halo of the Milky Way or clusters of galaxies or whatever, would still be in these mini halos. So at least some fraction of the dark matter would be in these mini halos. Other dark matter might be more diffuse. You know, the halos, not all the dark matter accretes on these mini halos. So the halos merge, then they get disrupted, so they can get diffuse again. But so some fraction at least would be in these mini halos. And the hierarchy of larger objects, you know, halos of mini halos and so on, formed through merger sequence. So dark matter would be clumpy. And these mini halos, you know, the first idea, if you have some clumped mass, is why don't we go and detect it through gravitational lensing, okay? Because gravitational lensing works the same way for all the mass. That's what Einstein said, right? Equivalence principle, doesn't matter if it's axions or baryons, the mass will deflect light the same way. Now, the problem is, of course, the difficulty is that these mini halos are quite small and diffuse, and when you calculate their surface density sigma, you know, mass per unit area, it's very small and much smaller than a galaxy or a globular cluster or anything like that. So it's only about 10 to minus 4 of the quantity we call critical surface density in gravitational lensing. So in gravitational lensing, we've got this thing. Here is the observer. There is some mass that deflects the light. There's a source of light behind. And the light, instead of coming to us on a straight line, gets deflected by the gravity of the lens, then comes to us this way, right? And if you want to make multiple images, right, so that you can also see a second image here, this deflector has to reach a surface density that is about the critical surface density, given by this expression, c squared over 4 pi g, and these are distances. Distance from observer to the source, from lens to the source, and from the observer to the lens, okay? So this critical surface density, when you put here distance of about cosmological distance, 3,000 megaparsecs or so, the horizon distance, it's about 1 gram per square centimeter. You calculate it. Okay, so the problem is these mini halos, they're much less than this, and that means that they will never produce multiple images, and if they magnify the source behind them, the magnification is only about this number, so you know, it's like 1 plus 10 to the minus 4. That's pretty hard to see, okay? So that's why they're hard to detect in this way. But these highly subcritical lenses may be detectable when you look at some lensed source very near caustics of larger scale lenses, okay? And then a very small change in the surface density can produce some observable effect. So caustics are just okay, so I have to go a bit fast. This is an example of a cluster that's lensing. There is a galaxy here in the source, one image. Sorry, this is not seen very clearly, but this is a critical line. Here is where multiple images appear, and this is a more detailed image of the cluster. So in this case, this is a galaxy behind, another image of the same galaxy, another image of the same galaxy. These two galaxies are coming close to a critical line. That's the critical line that's modeled, okay? And in the critical line, that's where you get the highest magnifications. The spiral arms of the galaxy are coming here. There's 2 copies of the spiral arms, one image, the other image. And right here, you get the maximum magnification. This is a blow-up of this. And here, what we observed here, we think is just a star at redshift 1.5, just a single star that was able to be detected by Hubble Space Telescope thanks to a magnification about a factor of 1,000. Okay, and when a star crosses the caustic, you can see it being hugely magnified. It follows a light curve that you can calculate precisely. Okay, that's very hard to see because it's very faint. But if on top of the cluster and the stars and so on, there is axion mini halos, you create perturbations, which mean the 2 images coming close together, they will be perturbed, and then instead of having a smooth light curve that you can calculate, you have some perturbations here that would indicate the presence of this clumpiness in the dark matter at very small scales. So, okay, I will stop it here. I see that I've run out of time. I just wanted to say, in this talk, you shouldn't use acronyms, so I put this acronym in my conclusions just as a joke. In my humble opinion, axions are the best dark matter candidate. And if true, they would be waves sloshing around galactic halos. So here I summarize my talk, and just let's go to the questions. Thank you.
Thank you, Jordi. There is time for a couple of questions.
Yeah, thank you for the nice talk. I found quite interesting. But I have a question. When you explain this Primakov effect, you say that there are some that from in the X-ray from the sun, and then converted actions, then converted back to X-rays. And since you said that the frequency of the action is not fixed in principle, scan a bit. So how can you distinguish an X-rays? I mean, this is where there is no action from the sun.
The actions coming from the sun would be highly relativistic, with energies determined by the temperature in the sun, and they would have a continuum spectrum. And you would basically be detecting the X-rays here, and you would see a continuum spectrum. Okay, but the actions in the dark matter, because they are at rest, then the frequency is essentially the frequency is just determined by this you see, mass of the axion. The velocities are about 10 to minus 3 speed of light. So gamma is 1 plus 10 to minus 6. The range of frequency is only 1 part in 10 to the 6, right? It's just a very, very narrow emission line because it's the axion converting to photon and giving its rest mass to the energy of the photon. So then it's a very narrow line, and nobody knows if the axion is true, it exists, you know, what is its mass and where the frequency would be. The day we find it, it will be very easy to detect it. But right now the difficulty is you just have these searches on a very, very narrow frequency range, and we just don't know where it is. So
there was one question over there, and let's finish this one with this question.
Thank you. Thank you, Jordi. I don't know if we have a lot of time, but I have two questions. So I'm going to start with the easy one. So if you showed us a drawing of YAXO, I just wanted to know if this is just one experiment located in one place, or is the idea to have many of these around Earth, or what's the...
YAXO is one of the experiments that is planned to look for axions. There have been already some in the past. The most important one was ADMX, that was done in the United States and has done this search. Then all other experiments try to look at other frequencies. There's many ideas for looking at different frequencies. I couldn't go into this, but basically YAXO is still a project, right? So it'll start working, we hope, maybe in 6 years, I don't know, but there's this prototype baby YAXO that's already being built. Eduardo Picatoste has been making a piece of it, this plate to read the data. Essentially, yes, so the plan, I think the plan is that maybe baby YAXO will start taking data around 24 or so, 23, 24.
Okay, thanks. A super short question. You showed us on your second slide different possibilities for dark matter candidates, and you had criticisms for the first two.
Yeah, in my humble opinion, and you can criticize me because I may be wrong.
Yeah, no, I'm asking you to criticize yourself, if possible. If you foresee any problem with this idea.
The axions.
Yes.
Well, actually, I think it all depends on this GA gamma, so the coupling of the axion to the photon. If you want to detect it in a physical experiment, it has to couple, and the stronger the coupling, the sooner you will reach to detect it. And if this coupling is very weak, we're out of luck. So it might be that the axion is real, and then if this coupling is very weak, maybe we have to think about the gravitational experiments, thinking there's mini halos, right? Maybe our ideas about axions are wrong, and you know they follow a different theory. I've talked only about the QCD theory, where this axion is related to the QCD, and it explains the strong QCD problem. And there's also other ideas for axions. So.
Okay, let's thank Jordi again, and let's move to the next talk.